All right, welcome back to the functions and relations slides. Let's keep on trucking and go down and talk about this new concept called relations, which is a new term, but I promise you know what this is. I promise you've seen it before. All right, it's just a name for something you already know. It's a very generic idea. A relation is like more generic than functions, so that's why we're studying it after relation, or we're studying relations after functions. That's why. So the way relations work is that they represent a relationship between two sets. They have some sort of relationship in common, and we're going to formalize it in a mathematical way using another kind of Cartesian product. So we say that a binary relation between two sets, A and B, so binary because there's two things involved, a binary relation between two sets A and B is a subset. We call it R. R is the name of the relation. It's a subset of A cross B. So again, just like functions, you're giving pairs of elements that are related. This thing from A is related to this thing from B. All right, where little a is in big A and little b is in big B. So to say that the pair AB is in the set R means that A is related to B under the relation R. All right, and then for reasons, we also like to write that ARB is a true thing. So like you make the relation, the name of the relation, like it goes in between the two elements that it's relating. So try to think about why that makes sense. It goes into some things that you already know, but like you can define a relation like this. You can say like, all right, these things are related in this way. Like x1, it's related to y1 in some way. And this relation is expressing that. X1 is related to y3 in some way. So this is not a function. You see that? It's mapping, well, if it were a function, it's like mapping x1 to both y1 and y3. But for a relation, it's fine. Just like x1 and y1 have something in common, x1 and y3 have something in common, and x2 and, let's say, y2 also have something in common. That defines my relation. So it's, again, it's a subset of the Cartesian product. So like here's x, here's y. It's relating those elements of those sets. And again, it's not a function. It does not have to do anything with a function. It's just saying that these elements are somehow related for some definition of relatedness to the other elements. It's very vague, very generic. A lot of things apply here. So here is this relation in picture form. So here's x1, x2, x3, and then here's y1, y2, y3, and y4. So this relation, R, is saying that x1 is related to y1. x1 is related to y1. It's saying that x1 is also related to y3, right? So really, there's no real arrow relationship going on. Oops. It's more like a line. Like x1, it's related to y1. There's no inputs and outputs, really. It's just saying that these have something in common, somehow. They're linked. x1 is also related to y3. They have something in common. They're linked. No arrows necessary. And then x2, we say, it's related to y2. So this is not a function. It doesn't have to x3 doesn't have to be related to anything at all. Okay? And you can have multiple things on the left side relating to other things. Like x1 is both related to y1 and y3, we say. Okay? So this is the relation R. All right? And so one way to write it is to use the name of the relation. If it's called R, you put it in between the two things that it's relating. So like x1 and y1 are related under R, so you can write it like this. You say that x1 R y1 is true. All right? x1 is related to y1 under the relation R. So it's a little weird to look like that, but that's okay. So I promise that'll make sense soon. But here's an example of a relation. So let's define this relation. Let's call it T. It's a relation T on Z on the left and R on the right. So integers on the left and real numbers on the right. And it relates them like this. X is related to Y under T if X is equal to the floor. That's the floor symbol. It's equal to the floor of Y plus 1/2. All right? So if this is true, X and Y, this is true about X and Y, where X is an integer and Y is a real number, then they are related under T. So let's try to write down some elements that are related under T. So like, really, it's easier to start with a Y. So like if 3.14 is on the right, what's it related with on the left? It's related with, well, you add 0.5 to 3.14 to make 3.64, and then you floor it. If it's 3 point anything, the floor of that makes 3. And so 3, do you see how 3 is related to 3.14 under this relationship? Because 3.14 floored is 3. So that's that. And then 5.67, let's try that one. 5.67 is related under t to what on the left? Well, 5.67 plus 0.5, it's 6 point something. And then you floor it, so it's just 6. See what it's doing? So this relation defines round to the nearest number. See what it's doing? 5.67 is getting rounded up to 6. 3.4 is getting rounded down to 3. I guess it's like a down arrow. So this relation defines what it means to round to the nearest number in terms of the floor function. That's kind of interesting to think about. So you can relate whatever you want. Here's one kind of relation. All right. Once you have a relation in mind, you can talk about it in a bunch of different ways. You can write it out as a picture. You can write it out as a set of pairs. There's other ways to do that. Here's another way. It's called a matrix representation of a relation. So this is another kind of picture. So a matrix representation of a relation between some set A and some set B is where you make every element of A a row and every element of B a column, and then you put like binary numbers inside. You put a 1 if there's a relation between those two things, and a 0 if there isn't. Right? So that you're going to have cardinality of A rows and cardinality of B columns, and you put a 1 in row R and column C, meaning that the A thing in row R and the B thing in column C are related to each other, right? Otherwise you put a 0. So here's a silly example. Let's say that we're going to make a relation called C between people and objects. All right, so here are some people. Lawton, that's me, I'm a person. And then NASA, let's pretend, is also a person. And then objects, things, just anything. Let's say that our set of objects are cars, cats, and spaceships. All right. And so let's define the relation C to relate people on the left to objects on the right. So C is a relation on people and objects. We say that P is related to O under C if some person P has an object O. So it's a has a relationship. So like, and you put a 1, so you're going to arrange all of your things on the left as rows and things on the right as columns. You're going to put a 1 if they align. So Lawton and car are related under this relation because I have a car. All right, and then Lawton and cat are related because I have a cat. So there's a 1 there, but Lawton and spaceship are not related under this relation because I do not have a spaceship, unfortunately. All right, they don't pay that much to be a teacher. Cannot afford spaceships these days. So that's just too bad. But NASA, on the other hand, I think NASA owns plenty of cars, right? Just to get people to the shuttles and stuff. So NASA and car are related. NASA, I don't think, owns any cats. Maybe they did experiments on cats back in the day, but I don't think they own any at the moment. So NASA and cat are not related. And then NASA and spaceship are related under the relation C because NASA owns quite a few spaceships. Yeah. So this is the matrix form. It's just you can read it off and see like what's related. Like NASA's related to both car and spaceship because it's got a 1 in those places. See that? And you can also spell it out as the relation, or as the just set of pairs thing, like Lawton and car related, Lawton and cat are related, NASA and car, NASA and spaceship. So you got a bunch of options now. All right, so that's another option, a matrix representation of a relation. All right, so we're still talking about binary relations. It's a relation on two things, two sets. Sometimes you're relating elements of one set to elements of the same set. So here's a binary relation on a single kind of set. So where that means it's a subset of A crossed with A. See that? A cross A. So it's relating things of A to other things of A, potentially. And so when you have a binary relation on a single set like this, where it's relating to itself, elements of A are related to other elements of A, then we call A the domain of this relation. Okay? So once you have the same thing being able to, like you have the domain of the relation, it exists, then you can have loops in your relationships because things can be related to themselves because what are elements of A but also elements of A? Yeah. So self loops are a thing now. Things can be related to themselves. Like if this is your relation, you can make, let's see. Like if this is your relation on elements, like your set A had elements x1 and x2 and x3, like you could relate, sure, x2 to x3 and x3 to x2, but you can also have self loops now because x1 can be related to x1 under your relationship. You see that? That's pretty cool. So that's a self loop. And then some binary relations that you know are like this. And now you know why we use this notation. Do you see it now? So less than is a relation. Does that make sense? What is it? Less than is a subset of R cross R, right? It's a relation on real numbers. And we like to do this, right? 2, 3, they're related, aren't they? They're in the set less than, where less than is the less than relationship. Because if 2 is on the left and 3 is on the right, 2 is less than 3. You see that? So this is just a generic idea that kind of wraps around the stuff that we already know and love. This is like saying, hey, is 2 less than 3? Yeah. It's in the relationship that's called less than. 2 is related to 3, where 2 is on the left and 3 is on the right. They're related under the less than relationship. It's just a set of pairs of real numbers. That's all less than is. Okay? Same with greater than. You could say greater than is also a relationship on real numbers. You could also say, like, I'm only talking about the greater than on natural numbers right now. So you're talking about pairs of natural numbers. That's totally fine. And you can be like, 5 and 2 are related under the greater than or equal to relation. Because, of course, 5, what does that mean? It means that 5 is greater than or equal to 2, and that's true. That means they're in the relationship, where 5 is on the left and 2 is on the right. The order is very important. See that? Order is very important. And then equality. That's also a relationship on numbers. You can be like, it's a relationship on real numbers. It could be, you could also define it to only be talking about natural numbers. You always have to define your domain. That's important. But equality, that is just a bunch of pairs of the same thing. It's a binary relation. We can talk about equality on integers. So it could be a subset of z cross z. So like -2 and -2 are related. They're in the equality relation. See that? Because -2 is equal to -2. That's the thing. Isn't that beautiful? So these are relations. You know them. Now you kind of understand this a little bit better. So, or just a generic relation, it's just a subset of a Cartesian product, where something's on the left and something's on the right. You can define any kind of relationship you want. This is like round to the nearest relationship, and you already know several. Less than or equal to, or greater than or equal to, equals. Those are all relations, all right? And now you know why this notation exists, because we're trying to copy what we know already, okay? So those are binary relations on a single set. And now that you know a lot of stuff, let's practice our knowledge. So, all right, here is a relation. It looks like this, and this is how you draw. You can totally draw relations like this. Like this is, you can call this relation R or something. And it says that like x2 is related. When you have arrows like this, it means that x2 is related to x3 on the right. x2 is on the left, x3 is on the right. And this arrow is saying that x3 is related to x2, where x3 is on the left and x2 is on the right. So if this is the relation R, this is saying that x1 is related to x1, and x2, this arrow right here is saying that x2 is related to x3. And then this arrow right here is saying that x3 is related to x2. See all that? So that's that one, that's that one, and that's that one. Okay? So that's the idea. I hope that makes enough sense. And now you can read this. Okay? So given this diagram now, see if you can find the matrix representation of it as well as a set of ordered pairs. So this is your relation, call it R or something. And it's a relation, it's a binary relation on the set A, let's say. And this is the set A. It has 1, 2, 3, and 4. Okay? So for example, these are the things that are related to other things. For example, 2 is related to 1 because there's an arrow from 2 to 1. Okay? So that's one thing. Those are two things that are related. So for example, 2 is related to 1 in this relation R. So that's one thing. See if you can come up with the matrix form of it, as well as like the ordered pairs form of it. Okay? So give that a try, and then I'll show it to you. All right. I guess it wants matrix first. So let's do that. So what are the things that are related to each other? It's 1, 2, 3, and 4 related to other things, right? One is related to itself, but you get the idea. So rows and then columns are both 1, 2, 3, 4. 1, 2, 3, 4, and then 1, 2, 3, 4, and you go row then column. So like this is saying 2, 2, 1 is saying that 2 is related to 1. It's saying, it's checking, hey, is 2 related to 1? And it is. So 2 is related to 1, so you go to row 2, column 1, and you put a 1 there, because they are related. All right, and then 1 is related to 1, so you go to row 1, column 1, you put a 1. All right, so those are those two arrows, and then let's see, 1 is related to 4, so you go to row 1, column 4, and then you put a 1 there. So row 1 is related to 4 in that order, because the arrows go in that way. Let's see what else. Then 3 is related to 2 in that order, so you go to row 3, column 2, and you put a 1. And then 3 is related to 3, so row 3, column 3. And then 4 is related to 3, so go to row 4, column 3, put a 1. And everywhere else, you put a 0. Let's see. I think that is what I wanted to say. So it kind of matches this idea. So that is what's happening, and I think that's what I wanted. Did I mess anything up? Let's see here. 4 is related to 3. Oh, sorry, this is 4 related to 4, isn't it? You go to row 4, column 3, and you put a 1 there. So I think that matches everything I wanted to do. So 0 is everywhere else because those things are not related. So for example, if there was a 1 right here, this would be saying that 2 is related to 3. And it's not. 2 is only related to 1, it seems. See that? In that order. That's why there's a 0 there. And then it's very easy to read this off as a set of ordered pairs. So R, the relation, is, you can just read them off. Like 1 is related to 1. Row 1, column 1. So that's the order, where the row is on the left and the column is on the right. So that's in the relation. 1 is related to 4. So that's a thing. 2 is related to 1. So 2, 1 is in the relation. 3, 2 is in the relation. 3, 3 is in the relation. Let's keep this all somewhat organized. So 3, 3 is in the relation, because that's on the next row. 3, 3, and then I guess 3, 2 as well. 3, 2 and 3, 3. And then 4, 3. See, that's also related. So that is the full answer. Okay, I hope that makes sense. Please yell at me if it does not. So, once we have relations on single sets like this, where there's something cross itself, relations on something cross itself, like this one, and these ideas of like less than, greater than, or equal to, equals, all those things. It's very common to have relations on single sets like this. All right, so we have some terms to describe those kinds of relationships. Of course, there's a million of them, as there is in this class, but it will make a bit of sense if I explain it, I promise. So let's pretend that R is a binary relation on a set A. So it's relating A's to other A's, potentially the same A, who knows. So we say that R is reflexive. It's reflexive if and every if. It's defining reflexivity. R is reflexive if and only if for every x in A, in your set A that you have this relation R on, if x is related to itself. So reflexive relations for every element, they are related to themselves. So it's saying like if 1 is an element of A, it's saying is 1, 1 in the relation. Okay? So that's the thing. So it's checking that kind of idea. All right, so let's see. How do I want to show you this? The less than or equal to relation is reflexive because every number is less than or equal to itself. Do you see that? If you're looking at another relation like the less than relation, and you're checking, hey, is it reflexive? You got to check that every number that you're relating is related to itself. So is every number related to itself under less than? No, because 1 is not strictly less than 1. So that's never true. So that's not true. But for like the less than or equal to, it is true. So less than or equal to is reflexive. This one is not reflexive. In fact, less than is called anti-reflexive. a relation is anti-reflexive if and only if for every x in the domain, x is never related to itself. See that? Because this is never true. Every number is never related to itself under the less than relationship. Do you see that? It's always false. It's never going to work out. So, yeah, if this is false, another way to say that's false is to say not. It's not true that x is related to x. And you can also write it with a slash, right? X is not related with a slash. X is not related to x. Just like I drew a slash here. That's just a normal mathematical thing. Okay? So that's anti-reflexive. Let's see, what else? I think, what else is anti-reflexive? I guess disequality, right? That's anti-reflexive. So this is always false, right? It's never true that 1 is not equal to 1 because it's always equal to 1. Then every number x is never not equal to x, all right? That's one way to think about it. So those are anti-reflexive relations. But this is a reflexive relation. Oops. All right, so that's when everything is related to itself. If it's reflexive, everything is always related to itself. If it's anti-reflexive, that means it's never related to itself. It's always not true. So that's reflexivity. Then we have symmetricity. We say that the relation R is symmetric if and only if for every x and y in this set A, then if x is related to y, then it must also be related. Then y must also be related to x, if and only if. So you better be able to go both ways. So if x is related to y, then y better be related to x, and vice versa. So if y is related to x, then it also better be true that x is related to y. So you better be able to swap the two. They always better be there. So if this is true, then this better also be in the relation. If these are related in that order, then you better be able to swap them, and they better still be related in that order. Okay, so that's the idea. Okay, so yeah, I'll give you some more examples on the next slides, but that's what it means to be symmetric. Let's just wait for the examples for now. I showed you a bunch of reflexive and anti-reflexive. I just want to say the terms first, let's say, and then we'll give some more better examples. All right, so antisymmetric is kind of the opposite of that. R is antisymmetric if and only if for every x and y. Then if you have both, if they can flip and work out, then the only way that could ever have been true is if x was equal to y. All right, if you have x related to y and y related to x, then it must have been that x and y were really the same thing. All right, you could never have separate ones. Okay, that's what it means to be antisymmetric. You really just not symmetric. If it looked symmetric, then it really wasn't, because they were just the same element. All right, so that's antisymmetric, and then here's transitive. A relation R is transitive if and only if, for every 3 elements now, x, y, and z in the set A. If you have that x is related to y and y is related to z, then you can skip over things. See how the y's agree? You can go straight from x to z. You better also have that x is related to z whenever this is true. That's what's going on there. All right. So it's kind of saying like transitive is trying to say like if you have that 1 is related to 2 and 2 is related to 3, you can skip over the 2 and get out that 1 is also related to 3. That better also be true. So that is transitive. All right. And just for a quick example of symmetric, like equality is symmetric. Like if 1 is equal to 2, then of course 2 is equal to 1. That's the idea. So I have plenty of examples on their own slides now. Okay, so if that made no sense at all, I just wanted to say the terms. They are weird. I promise that it will make sense with more examples though. All right, so let's talk about reflexivity and anti-reflexivity. All right. If you stare at the definitions long enough, what reflexivity means is that every element is related to itself. If you have some relation on a set A, then every element better be related to itself. Okay? So here's an example. Let's say that we have a set A and we're going to define a relation on this set A. Okay? So here's some example elements. Let's say that this is what is in A. And if you have some relation on the set A, these arrows define the relation. It's reflexive if every element is related to itself. So you're looking for all of these, right? These better all be here. All these individual elements of A better be related to themselves. And that's what it means for the relation to be reflexive. Gosh, there's too many terms, I know. So This is what it means for every element to be related to itself. That means it's reflexive. All right, this is a reflexive relation because of those green arrows. All right, so less than or equal to and equal to are reflexive relations because every element is always related to itself under these relations. So like 2, for example, is less than or equal to 2. This is always true for any number you could put on both sides of the less than or equal to because you got the equal to part. That's the thing that's making it reflexive. And so naturally, equality is itself reflexive because every element is related to itself under the equality relationship. All right, I hope that makes sense. And then anti-reflexivity means that no element is related to itself. That never works out. For every element, there is never a self loop. It's never related to itself. So our strict comparisons, like less than, and strictly greater than, those are anti-reflexive relations because you pick any number, you put it on both sides of a less than, it's never true that 2 is strictly less than 2. It's never true that 4 is strictly greater than 4. See that? Any number could go here. It's never true. They're anti-reflexive. All right? So that's what it means to be reflexive and anti-reflexive. All right? So let's next talk about symmetric and anti-symmetric. So again, if you stare at the definitions long enough, a relation on a set A is symmetric if you can swap. If you can always have the opposite once you have one side. You're allowed to swap x related to y and y related to x. It means the same thing. The order doesn't matter at that point. So you can always flip it around. So if this is your set A, and you have these elements in your set A, and like here is a start of the relation, you know that this relation is symmetric if whenever you see an arrow, the opposite arrow also exists. So in order for this relation to be symmetric, this arrow better exist, this arrow better exist, and you better also be able to flip this one too. That arrow better exist. Do you see that? That's what it means to be symmetric. You can go in either order. Either this is related to this one in that order, or this one is related to this one in that order. They're related in either way. That's what it means to be symmetric. You can swap, all right? Technically, this means you don't even need arrows because the direction doesn't matter. You just have one big thing connecting them both, and you can go in either direction. That's what it means to be symmetric, yeah? So equality is a good example of a symmetric relation, all right? So if you know that x is equal to 2, of course, 2 is equal to x. It means you can flip it, and it means the same thing. It's still true. You see that? So that's reflexive. And then also, here's like a relationship under like family. So like the is related to relation is symmetric because if like I have a sister, if I am related to my sister, then my sister is also related to me in that order as well. See that? If I'm related to my mom is related to me. See that? You can flip it around like that. That's totally fine. So those are symmetric relation examples. And then anti-symmetric relations are when you cannot have both. You can't have x related to y and y related to x when they're different, all right? It's only ever like one's related to the other or none, okay? It's only ever one or none, all right? So you can't have both x related to y and y related to x when y and x are different. That's what this definition means. If you got pairs of things and you know that one's related to one in that order and the vice versa is also true, that must have meant that they were equal. You couldn't have had both and have them really be different, okay? So I think some examples will make that one make more sense. So less than, for example, is an anti-symmetric relation because 2 is less than 3. You can never swap it and have it be true, right? 2 is less than 3. It's never true that 3 is less than 2. You can't swap it. It's always if and only if, right? 2 is less than 3 if and only if it's not true that 3 is less than 2. They're anti-symmetric. Once you have one, you cannot have the other. See that? That's what's going on there. And then, let's see. Is older than is an anti-symmetric relation because it only goes in one order, just like less than or greater than would. So, for example, like, I don't know, I'm a brother, and I am 31, and I have a sister, and she is 29, and I am older than her, right? So it's true that brother is older than sister under the is older than relation, But do you see how, like, once you've said one side, it's never true that the other one's true, right? It's never true that sister is older than brother with this kind of relationship. You see that? So is older than, it goes one way. You only got one way. It's not reversible. Okay? So that's what it means to be anti-symmetric. It's only ever one or none. So that's that one. But symmetric means you can flip them. All right? Equality is totally symmetric. So if a brother is related to a sister, then the sister is related to the brother. That's fine. These ideas are anti-symmetric. All right? So that's that one. And now let's talk about transitivity. Transitivity is like the last piece of the puzzle. So this one means, like, if you have three elements now, you can skip over. If you know that x is related to y and y is related to z, then you must have that x was related to z. You could skip over the y's, essentially. Okay? So it's this kind of thing that I drew here, but let's spend some time talking about this one. All right? So plenty of memes about this stuff, of course. So transitive relations allow you to line up two things in your relation and conclude that a third thing is true. It's like saying, if you have this one, x related to y and y related to z, then you must be able to skip over. Like, you better be able to, like, have these align, and you can skip over all the way from x to z. Then you must also have that x is related to z, also holding in the relation. Okay? All of these mathematical relations are transitive. All right, let me show that too. So, like, less than, for example, is a transitive relation because if I know that 2 is less than 3, and I know that 3 is less than 5, those are both true things, right, related under the less than relationship, then I know that 2 is less than 5. Do you see that? These align and go from here straight to here. They lead to that. That's what it means to be a transitive relationship. So if you have both of these, you can go in one fell swoop straight to concluding that 2 is less than 5. Less than is a transitive relation, so are all of these, right? Is related to is also a transitive relationship. If I'm related to my sister and my sister's related to my mom, then I am, of course, related to my mom. You can go in that order. It's totally fine, all right? There's some way for you to get there, okay? So this is essentially what transitivity means. You have a set A, and like, you have some elements of A. You have some initial arrows, let's say. If you have these arrows, for example, in order for this to be a transitive relation, once you have one thing related to another, and then that second thing related to a third thing, you must be able to go in one fell swoop from here all the way to there. So this better also exist. All right? You better be able to go from straight there to there. That's what it means to be transitive in picture form. That's this idea. Okay? This one by itself, it has no arrows. It's okay. Don't have to add anything else. So this is an example of a transitive relation, all right? And so, I don't know, is in love with, if you think about that. That's not a transitive relation sometimes, and that makes for good drama. So, all right. So that is what it means to be transitive. I do want to say something. There's a strong relationship between all three of these. Like, that's why we're talking about them. Reflexivity, symmetricity, and transitivity. Those are the key ones I want you to remember. The anti ones doesn't matter too much. But these normal ones without the word anti, they are very, very important. All right? Here's one cool thing. This is like an aside. I won't test you on this idea, but it's a cool idea if you think about it. If you have a relation and you know that it's symmetric, symmetricity plus, and you know it's also transitive, if you know it's both of those, symmetricity plus transitivity, that gives you a weird kind of almost reflexivity. I'll call it pseudo-reflexivity. Pseudo-reflexivity. Let me show you why. So if you have, for example, this is your set, and you have a relation on it, and you know that this is true. You know that it's symmetric, so if you have this arrow, you must have this one. And then you know that it's a transitive relation, so that means if you have this arrow and this arrow, you can go straight from there to there, which is it to itself. You see that? And then also this one. If you have this arrow going this way, going there, and then this arrow back, you should be able to go straight from this element to itself. So again, you have a self loop. And these self loops give you reflexivity. So if you have a relationship where there's always something is at least related to something else, and you know that it's symmetric and transitive, you essentially get reflexivity for free. The only way that this falls apart is if you have an element over here that's not related to anything at all. Then this does not give you for free reflexivity on this. It needs to be related to at least one thing, and that unlocks reflexivity, which is kind of cool to think about. So it's almost reflexive, which is fun. So that's a little mathematical idea for the day. So, okay, I've shown you way too many terms. I'm sorry, that's just the nature of this class. But I'm going to give you some example relations, and I'd like you to tell me whether or not the relationship is reflexive, anti-reflexive, or neither, symmetric, anti-symmetric, or neither, and then transitive or not transitive. All right, there's no like anti-transitivity or anything like that. Thank goodness. So, okay. Here are your two relations. Give them a try, and I don't know the best way. Let me explain them both. Let's write them out, and then I'll let you try it. So the domain. Let's say that we're making a relation T for part A. The domain is a group of people, so we're relating people to other people, and we say that under the relationship T, X is related to Y if Y, the person Y, is taller than person X. So like that's the taller than relationship. Okay? And you can assume that there are at least two people in the group who are not the same height. All right? So tell me, is this a reflexive relationship, anti-reflexive, or neither? This is taller than a relationship. Is it symmetric, anti-symmetric, or neither? And then is it transitive or not transitive? So do that one. And then do the same for this relation. So let's say that this is a relationship on two numbers, pairs of numbers. So you say that AB is related to CD if A is less than C and B is less than D. All right? So give both of those. And yeah, so see how far you can get, and then you can unpause the video. I'll give you hints slowly but surely. But here are the definitions of all of those things. And I'll scroll very quickly through all my examples so that you can pause if you need to and confirm your suspicions. Okay. So let's tackle part A first. So this relationship is like if Y is taller than X. It's like a less than relationship, really, isn't it? It's like X is X T Y is if Y is taller than X. So it's like is like less than X. That means X is shorter than Y. See that? Something like that. So it's trying to ask this question. Well, is it reflexive? First question. Is it ever true that like person A is on the right taller than person B, or person A being smaller than themselves? Is that ever possible? No, I don't think so. So that means, if you think about it long enough, that means it's anti-reflexive. You see that? A person cannot be taller than themselves. It's impossible. So it's totally anti-reflexive for the first one. It's never true. I hope you see that. And then let's think about symmetricity. So, all right, if I know that if person A and B, people A and B are related under the taller than relationship, that means B is taller than A. It's like this. A is shorter than B. Do we know then? Can we immediately conclude that the opposite is true? That's what it means to be symmetric, right? Does it mean that if we know that A is shorter than B, does it mean that B is shorter than A? I'm pretty sure that's never true, right? So if it's never true, that means it's anti-symmetric. It's anti-symmetric. And then what about transitive? If I know that A is shorter than B and B is shorter than C, can I conclude that A is shorter than C? So this is kind of like the less than relationship. And you can, can't you? You totally can for any elements that work like this. So I know that A is shorter than B and B is shorter than C. Like C is very tall. C is taller than both B and A. So of course we can conclude this. You see that? It's like a less than relationship. And so it is a transitive relation. And I hope you see that. So that's a silly example there. Here's a more mathematical example. So if this relationship is on integers, whole numbers, could be positive, could be negative, could be 0. We say that AB is related to CD if A is less than C and B is less than D. So what are some examples of things that are related under this relationship? Like, is it true that it's a reflexive relationship? Let's write it out. Like, is it true that where do I even want to put this? Is it true that, like, I don't know, if I have 1, 1, is that related to 1, 1? Stuff like that, because it's the same, or they don't have to be the same element. Actually, it could be 1, 2. Is that still related to 1, 2? Or these should be standing in for any element. We're trying to prove a for all here right now. But all right, are these related? Well, they're related if the first thing is related to the first thing on the first side is related to the first thing on the second side. So if this is less than or equal to this, yes it is. And then is this less than or equal to this? Yeah, it totally is. So I'm thinking it's reflexive. Do you see that? If you have two things, it's reflexive if this first element, these first two elements, they're related under less than, and same for the second two elements. If they're related under the less than relationship. So that totally works out. See that? So it's totally reflexive for that reason. And then let's talk about symmetricity. So is it, let's see, how do I want to do this? If I know that A and B, we're going to have to use variables this time, are related to C and D under the relationship R, then can I conclude that, is it possible to go to a conclusion that C, D is related on the left to A, B on the right? All right, is this ever possible? Well, this is true. We know that this is true by the definition, right? If this is true, if we know that A, B is related to C, D, that means that A is less than or equal to C and B is less than or equal to D. See that? And if I want to conclude this side, I have to show that C is less than or equal to A and D is less than or equal to B. You see that? When can you conclude this? Well, it's not always the case, right? If this is a 1 and this is a 3 or something, then the 3 and the 1 never make it true. See that? It would never work out. So this is not always the case. You cannot flip it like this. In fact, the only time you can flip it is when they're equal. See, like, the only way that you can flip a less than or equal to into a like essentially a greater than or equal to, the only way you can flip it like that is when the numbers were equal to each other. And that is the textbook definition of anti-symmetric. All right? That's what's going on. We go back to here. It's like, all right, if they ever were, if you ever could swap them like that, that means they were equal after all. And that is what we're concluding here. So they're anti-symmetric again, just like the example A. Okay? I don't know if that makes some sense. These are definitely harder relations, and I want to get your brain hurting a little bit on them so that you learn these ideas. And that the book makes more sense when you read it now. So that's an anti-symmetric relation. Then finally, let's figure out, is it a transitive relation? All right? So let's see here. Well, how do I want to say this? Is it a transitive relation? Well, it is if you can conclude the following, right? Let's see. Let's make up an example. Let's use this corner right here. So, all right, if it's transitive, I have to have two things that are related. So I need 2, 3. Let's say that that's related to, let's find something that it is related to. So it's like, it's related to 3, 3, right? Because 2 is less than or equal to 3 and 3 is less than or equal to 3, that's fine. And then I need to start with the 3, 3, right? This should work for anybody. We're trying to generalize this idea, but we'll try some examples to convince ourselves. What's 3, 3 related to? It's related to like 4, 5, let's say, because 3 is less than or equal to 4 and 3 is less than or equal to 5. And then in order for this relationship to be transitive, I need to be able to go straight from here to here. I need to know that 2, 3 itself is related to 4, 5. And is it? Well, yeah. 2 is totally less than or equal to 4, and 3 is totally less than or equal to 5. And so if you spelled this out, if you used variables, and you put together everything you knew, because like this is less than or equal to this, and this is also less than or equal to this, then for sure the starting point is less than or equal to this starting point, and same for the second index. Okay? And that satisfies the relationship that we're defining here. All right? So it really is going to end up being a transitive relation. Once you have these things like this, and if they agree on the last thing here and the first thing here, you really can go straight from the first to the last. You can conclude it like that because it's using underlying less than or equal to. and less than or equal to is totally a transitive relation. All right, it's just using it twice, essentially. Okay? We learned that already. So these are some harder examples for sure of symmetricity, reflexivity, transitivity, all that fun stuff. But hopefully, now that you've scratched your head a bit on them, the book will make more sense, your homework will make more sense. But please yell at me if it's too confusing. I know this is definitely one of the harder topics, so it's very vague. But hopefully you're getting it a little bit. A good thing to talk about next is kind of going back to these arrow kind of diagrams, and hopefully my PowerPoint is happy with me right now. It is frozen. Hopefully you can still hear me right now. Okay, there it goes. So this kind of diagram with arrows and dots, it's called a directed graph. All right, that's its fancy term. All right, so let's define that, because we've been using those as we're drawing relations. We've been drawing, these are called directed graphs, these things with dots and arrows. So let's spell out what those are. We're going to study graphs in general later in a future chapter of the book. So yeah, let's talk about directed graphs for now. So a directed graph, or digraph for short, because people don't want to say full terms, like they took the die part and they took the graph. So a directed graph or a digraph is a set of two different sets. It's a pair of things, a pair of two sets, a set of vertices and a set of edges. All right, so V is your set of vertices. It's the things that you're relating, things that you're drawing arrows between, and then edges are your arrows. It's a set of V cross V. It's a set of pairs of vertices that you're connecting under your arrows when you draw your picture, okay? The set of edges that connect your vertices. So we say that digraphs, or directed graphs, they're used to relate things, to represent relations. They're used to represent like roads, like maps are technically a digraph, cities, etc. And you like to move around. So here's an example of a directed graph. So like here's cities, it's like a map. So San Francisco, San Jose, Fresno, SLO, Santa Barbara, LA, all those things, those are your vertices. All right, those are things that can be connected over arrows. So that's our set V. And then E, our set of edges, are arrows in this graph. So like there's an edge from Fresno to SLO, because that's like, I don't know, the 41 to the 101 or something. You can drive from there to there. There's a road in that direction. Okay, you can go straight from there to there. There's a road from Fresno to LA. Okay, so that's saying that they're connected in that order. So that's the relationship. Those are the edges. And there's also like San Luis Obispo, Santa Barbara is in there. San Jose, San Francisco is in our digraphs edges set. All right, because that's an edge from that one to that one. It's always from left to right. And so in a digraph, it's natural to move around, just like we were moving around for our relations and things. So we've really been drawing directed graphs this whole time. And moving around, a digraph draws what's called a path, which is a very natural term. So there's a path, we say, if you can follow edges to get from somewhere to somewhere else. So like Fresno to LA, there are two paths to get there. There's one straight path, just one edge, and there's one like 3-edge path to get there. See that? There's a path from Fresno to Santa Barbara. You can go through San Luis Obispo. There's a path from Fresno to San Francisco. See that? Because you can follow edges to get there. So it's a very generic idea, but that's what it means to be a directed graph, and that's technically what we've been drawing when we drew relations. So it's worth talking about for at least a little bit. All right. With that in mind, all right, let's go back to pictures. We'll draw some more digraphs now that we know what they're called. Let me tell you about the composition of relations. So just like you can compose functions, you can totally compose relations too. All right. Of course, my PowerPoint wants to freeze right now. Hopefully, again, you can still hear me. Let me know if you can't, and I'll re-record this or something. But yeah, just like you can compose functions, you can compose relations. All right. It looks a little bit different, but it still makes sense. So we say that the composition of two relations, R and S, they're both relations on a set A, mind you. When you have two relations on a set A, call them R and S, you can make their composed relation, S after R or S composed with R, and it's another relation on that set A, okay? And here's what it means to be in the composition. You say that A comma C is related under the composed relation, S after R or S composed with R, if and only if, oops, I don't know how I clicked that, sorry, if and only if you have three things, and you've got that A comma B is related under the R, like you do that one first, and then B comma C is related under S, you do that one second, and they like agree on the B, the thing in the middle, okay? So just like for functions, you go from left to right, like you find something related under R, and it's related something to a B, and then you go into S and you find like what's related with B in the front, because they agree on this middle thing. And then once you have both of these in the composed relation, you can go straight from A to C. They are now related. All right, so here in picture form, this is what this is. If you have elements A, B, and C in your set, and you know that A is related to B under R, like you do that one first, and you know that B is related to C under S, then in the composed relation, you have a relationship between A and C, straight from there to there. So this is S after R, or S composed with R. Okay? So just like for functions, you work from right to left, and let me give you a concrete example of that. So let's define two relations, S and R. So, and they're going to be relations on a set containing A, B, C, and D. So let me draw that in some order. Let's say that this is A, this is B, this is C, and this is D. And let me, because I have an S relation and an R relation, let's say that the relation S is going to be in blue. Well, here's my key to this drawing. So S is going to be in blue, and then I'll use green to draw the relation R. Okay? So let's do S first, though. Let's write out all the arrows. Let's draw the digraph. So A is related to B under S. Boop. A is related to C under S. C is related to D, and C is related to A. So we got that under S, and then under R in green, we have B related to C. So boop. We also have that, I don't know the best way to do this. Then we also have that C is related to B, so you can go backwards as well. That's a thing. I don't know how to make these straight and then not overlap. Sorry, I'm going to have to overlap a little bit. There. I have both of those. I have A related to D. So essentially like that. And then also D related to B. So I can go straight from here just like that. Okay, so that's my relation R. And if we're going to do the composition, if we're going to try to do S after R, or S composed with R, you're going to go and find stuff in R first. You're going to follow things in R, see where they overlap, and then follow another arrow of S. And anything that's combined like that, you can say are related under the composition. So let me redraw the set in rainbow, and then I'll draw in as rainbow arrows, let's say, the composed relation. So here's A, B, C, and D again. So, okay, what you do when you're trying to find the composed relation, you follow arrows of R first, and then you see if there's anything coming out. That's an arrow of S right after that. So like this is an arrow of R. It's a green arrow. And then you find, are there any S arrows? Are there any blue things coming out of here? No. So that's not helpful. So I'll keep going. Then I'll try this arrow. That's an arrow of R. Are there any S arrows coming out of B? Any blue arrows coming out of B that I can follow? No. And then what about this one? That's an arrow of R. Are there any S arrows, again, coming out of B that I could follow? No. So that leads to, there's only one arrow I haven't tried yet. It's this one, this green arrow. So I follow this one, it gets me to C. Are there any blue arrows coming out of that? Yes. There's one here that goes from C to A. So I went from B to C under R and C to A under S. So that means that I'm relating. I can go in one fell swoop from B all the way to A in the composed relation. So that means there's an arrow from B to A in the composed relation. I'll draw that in rainbow here. All right? And then also you can go by green to get here again. Now we're in C, and there's another blue arrow. There's another S arrow out of C, from C to D that I can follow. And that takes me straight from B all the way to D. And that is now related under the composition as well. It's this, like an arrow this one, an arrow this one, then that is related straight to there under the composed relationship. So B is related to D, and those are the only two things related under that composed relationship. Okay? So that's how you compose them, and hopefully that made a little bit of sense. Here's a fun idea. if you compose a relation with itself, like you compose just S with itself, it's essentially you're following like an S and then another S arrow. You're following two S arrows, and that is in the composition thing. Okay, so if you compose a relation with itself, you're essentially just finding all length 2 paths, like you're following two arrows. You're finding a length 2 path, in the graph of that relation. That's pretty cool. It's like this would be in the S composition with S, because you could follow this arrow, then you can follow that arrow right after it. That's kind of cool. So similar to that, last thought of the day, that leads to a concept called closure. Certain kinds of composition leads to closure, and it's just a more generic idea. So let's talk about closure as the second to last slide. And I need to say some words again, of course, but I have plenty of examples on the next slide, so just wait till the next slide. I promise we'll get there. But let's see. Sometimes we have a relation, and we know how nice it is to be all these things. We know how nice it is to be reflexive, symmetric, transitive, all those nice terms that we can describe relation as. Maybe we have a relation and it's not quite one of those things. It's not reflexive, but we'd like it to be reflexive. It's not symmetric, but we'd like it to be symmetric. It's not transitive, but we'd like it to be transitive. There's a way to take your relation and add the minimum amount of stuff to it, the minimum amount of arrows to it, that makes it what you want it to be. You can create the smallest possible relation that is the same as R, but then also reflexive and symmetric and transitive, or some combination of those. Okay? So what it's called, when you modify R in this way to be what you want, like you wanted it to be reflexive, then that means what you call that is you've made the reflexive closure of R. If you modified R to be symmetric, you've made the symmetric closure. If you modified it to be transitive, you've created the transitive closure. All right, so those are the new terms. So if you want the reflexive closure, you just add every self loop. And for every x in the domain, make sure it's related to itself. That's what it means to be reflexive. All right. So a good example of that, like the reflexive closure of less than, is just like everybody's got to be related to themselves, so it becomes less than or equal to. So think about that once I show you an example. I promise it'll make sense. So that's reflexive closure. And symmetric closure is the same idea. Like you have a relation and you want it to be symmetric, so that means if you have an arrow from x to y, you better add an arrow from y to x if it's not there already, because that's what it means to be symmetric. You better be able to flip it. Yeah? And then transitive closure, the final idea, is that if you have two arrows, an arrow from x to y and an arrow from r to z, if x is related to y and y is related to z, then you better add an arrow. If it's not already there, you better add the fact that x is related to z. And this might give you more arrows that you'd have to add through transitivity. So this is the hardest one to do, I would say, transitive closure. You have to keep doing that. It's like a loop until there's nothing left to add. All right? So that's the idea. So the transitive closure has to do it's very close to relations and their composition. So in terms of graphs and digraphs and things, what you do is, if you want the transitive closure, you add an arrow from x to y if there's any kind of path from x to y in the original relation. All right? And I'll show that to you in an example on the next slide. All right? So that's an easy way to compute the transitive closure. You just gotta keep checking yourself, and eventually you will finish. Though it does take a while. All right? So let me show you these examples. Let's compute these closures. All right? So here's the same relation a couple times, and let's make it these things. Let's find the reflexive closure of this relation. All right, so here's the original relation. It's relating 1, 2, 3, 4, and 5 in some way. If you want the reflexive closure of a relation, you add every element related to themselves. So you add x related to x all day long, because that's what it means for a relation to be reflexive. So I need to add a bunch of self loops in order to make this relation reflexive. Do you see that? That's the minimum amount of work I need to do to make sure that this is a reflexive relation, because every element better be related to itself in addition to whatever else is already there. So I have created the smallest new relation that is also reflexive. You see that? So this is called the reflexive closure. All right? Likewise, the symmetric closure of a relation, if this is my original relation, what the symmetric closure means is if I have x related to y in my relation, I better add y related to x if it's not there. I better add this, y related to x. I better be able to go the other direction. So if I have this arrow from 1 to 2, I better also have an arrow from 2 to 1. If it's not there, I need to add it to be there. Okay? Same with this. If I have an arrow from 2 to 5, I better have an arrow from 5 to 2. I better be able to go in the opposite direction. If 2 is related to 5 in that order, then 5 better be related to 2. That's what it means to be symmetric. I need to add all of these arrows, and now it's a symmetric relation. You see that? That's what's going on, all right? So those two are pretty easy. Transitive closure, that's the last piece of the puzzle. That's the hardest one, all right? So what you do, if you want transitive, you just think about it this way. If you have x related to y and y related to z, if they line up, you have x related to y and y related to z, that's like an arrow from x to y and an arrow from an arrow from y to z. You better add an arrow from x all the way to z if it's not already there, all right? And so that's going to lead to an easier way to think about that is like just add an arrow if there's a path at all in the original graph. And so that's kind of like eventually I'll be adding an arrow all the way from 1 to 3. Do you see that? But let's use this rule to compute that. I'll show you it both ways. So for example, I have 1 related to 2 and 2 related to 5. Do you see how 1 related to 2 related to 5, they line up like that? So I better add that 1 is related to 5. I can go straight to there under the transitive property. All right, so under transitivity, if I want this relation to be transitive, if I have these two arrows, I better have one arrow straight from there to there. See that? And that will unlock more arrows, in fact. Let's just do the red ones first. So again, if I have this arrow from here to here and this arrow from here to here, they meet in the 5 in the middle, then I better be able to go straight all the way through from 2 to 4. So I need to add this arrow, all right? And then one more made from the red arrows. If I have the ability to go from 5 to 4 and 4 to 3, it's related like this, and I better be able to go straight from 5 to 3. Okay? And so those I added, and it's still not fully transitive, because now the blue arrows come into play. See this? Now if I follow a blue arrow and a red arrow, if I go from 1 to 5 and then 5 to 4, that means I better add a way of going straight from there to there. Straight from 1 to 4 now. See that? So I need to add this one, and likewise, let's see, what else do I need to add? If I'm able to go from 2 to 4, and 4 to 3, I better be able to go straight from 2 to 3. Straight from 2 to 3, just like that. So I need to add this arrow in order for it to be transitive. And then let's see, so if I can go from 1 to 4, that's this one, and then 4 to 3, I better be able to go straight from 1 to 3. I can go all that way. So that's that arrow that I was talking about at the beginning now. I have to add that one. And then let's see, have I added all of them? So I should be able to go from 1 to 2 to 5 to 4 to 3. Should also be able to go from 2 to 5, 2 to 4, 2 to 3, 5 to 4, already there, and 5 to 3, and then 4 to 3. I believe that is everything. I'm just double checking myself because this is the hardest one to remember and get right. But it's essentially, if there is a path at all, there's a way to get like from 1 all the way to 4 in the original graph, I will eventually be adding an arrow straight from 1 to 4. That's essentially what's going on. So there was a path in the original graph all the way from 1 to 3, so eventually I was doomed to add an arrow from 1 to 3. Okay? So that's what it means to be the transitive closure. I've started with my original relation. This is the one where you have to add the most new things, but I've made the smallest new relation. That's the same as the old one, but now it's guaranteed to be transitive. I've added everything that transitivity requires, all right? The smallest amount of things. So that is the transitive closure of a relation. So you can do all of these. You can do any combination of these, but now you know how to do each one individually. And so that was a lot of new terms. So thank you for sticking with it. Do practice this by reading your book and doing the homework. But that is our first taste of relations, and that's where I would like to stop for now. This is like a 3-lecture set of slides, and we're a little bit in the middle right now. So we'll come back next time and finish these up.